reviewed Conjectures and Refutations when it first came out. Sir Carl was not amused by the review. Since I come from a country where the president misquotes very often, I'm going to begin. I've learned from him. I'm going to begin with two misquotations. One is from Leonardo, who says that simplicity is the ultimate truth. He didn't quite say that way, but that's what he meant, I assume. Simplicity is the ultimate truth. And the other one is from Samuel Johnson, who says simplicity, like patriotism, is the last refuge of a scoundrel. I left out like patriotism. I don't think he would have appreciated that. But yes, simplicity is the last refuge of a scoundrel. Now, the quote or misquote from Leonardo is one that I think that 99.44% of philosophers like. That's what they think. They think that simplicity is the ultimate truth, or at least the ultimate sign of truth, and practically nobody thinks that simplicity is the last refuge of a scoundrel, except for your humble lecturer today. And that's what I want to get you at least to think of your opposition if you're a Leonardo aficionado, if you're a Leonardo lover. Look, some of the greatest scientists, including Newton and Einstein, and some very important philosophers, invoke simplicity in defense of a theory. Newton and Einstein do so for two reasons. They both claim that nature is simple, and that the fact that a theory is simple is at least some evidence that it's true. Philosophers are less likely to make the first claim and very likely to make the second. Despite the popularity of these views and the evidence that they're defenders, I want to urge you to reject them, or at least to cast a dubious eye in their direction. Now I have this thing. Let's see where we are here. I'll start with Newton, although this is from, as Joe said, it's from a book where I consider the various roles that simplicity is supposed to play according to people who love simplicity. And today I'm just going to consider two, the ontological and the epistemic. All right, these are the various roles they're supposed to play, but we're going to look at ontological, epistemic, underdetermination, presupposition, and all that jazz. Let's look at Sir Isaac, who says that nature is simple and does not indulge in the luxury of superfluous causes. But I like the earlier translation better. Nature is simple and affects not the pomp of superfluous causes. That's magnificent. I don't like the later 1990s translation of this. Let's look at, if I have them here, and then nature is always simple, ever consonant with itself. Okay. Oh, and there's Einstein. Yeah. As science progresses, apparent chaos is resolved into a sublime order that is to be attributed not to the rule of the individual mind, but to the constitution of the world of experience. This is what Leibniz so happily characterized as pre-established harmony. Okay. Let's see what's next here. Good. Okay. Now, Newton, as some of you may know, in the Principia, his most important work, of course, is done in Book 3. That's what he aims to prove, namely the law of gravity. And he begins, interestingly enough, with philosophy. And he begins with 4 rules of reasoning in science. And here are 2 of them. No more causes of natural things should be admitted that are both true and sufficient to explain their phenomena. And therefore the causes assigned to natural effects of the same kind must, so far as possible, be the same. Newton crucially needed these 2 rules. And he used them in the actual proof of the law of gravity. And then this is to be followed by the next 2 rules. This is the inductive rule. Those qualities of bodies that cannot be intended and remitted, don't worry about that phrase, and that belong to all bodies on which experiments can be made should be taken as qualities of all bodies universally. That's his version of induction. It's more powerful than induction, but that's what he wants to say. And the fourth rule I'm not going to make reference to. Okay. Now, nature is simple. And affects not the pomp of superfluous causes. Nature is simple, and therefore the universe is the same all over. It's a terribly vague phrase. Nature is simple. What does it mean? Now Newton, like Einstein, never defined simplicity. Einstein says he knows it when he sees it. He actually says those words, and Newton really, I think, agrees with that sentiment. My concern is not so much with defining simplicity. I didn't even know how to do it. Philosophers used to be interested in this back in the 1960s and 70s and so on. But to me, that's not the interesting thing. The interesting thing to me about simplicity is what you do with it. What claims you're going to make with it, and why you make those claims. So, what do you do with the claim, nature is simple? Given that it's terribly vague. Well, why is it vague? Because there are different respects in which nature can be simple, and they don't all march together. Newton mentions, too, the number of different causes. For example, forces postulated, whether there are different laws for different parts of the universe, and so on. Einstein mentions just simplicity in mathematical equations. Are there others? For example, not just whether there are different laws for different parts of the universe, but the number and complexity of the terms in those laws, not just the number of different forces, but the number of different basic types of objects in the universe. Is nature simple in all of these ways? In some of them? Which ones? And then another question, how simple is nature? There are different degrees possible, more or less simple. Newton and Einstein don't say. And also, even more importantly, it's description relative. There are different formulations of the same theory, for example, Newtonian mechanics, some of which are much simpler than others. Okay? Even in mathematical simplicity, look, the shape of a petaled flower, okay, so-called polar rose. Now, it's very simple if you give the equation in polar coordinates, and much more complex if you give the equation in Cartesian coordinates. Okay? So is the shape simple or complex? Well, it depends on the way you formulate it, the way you represent the shape. And then also it's level relative. At what level is nature simple? Some say simple at the level of fundamental particle physics and complex at the level of macro systems. But the standard, so-called standard model in physics, in particle physics, has a zoo of fundamental particles and four unrelated forces. And classical thermodynamics, as a macro theory, has very simple laws relating a few simple properties, while underlying statistical mechanics introduces more complex equations involving both attractive and repulsive intermolecular forces. String theory, the ultimate theory, introduces a simple ontology of entities, namely one, strings, vibrating. But what do they vibrate in? They vibrate in 10 dimensions of space-time. That's a lot of dimensions. We've never seen 6 of them. Okay? And in fact, string theorists will tell you, yeah, that's one of the problems with string theory. You can't test it. He hasn't any way of testing it yet. Okay. So there are two, let's see where we are now. Here's all the nature of simple issues that I just went over. And then you could take two attitudes here. You could take a localism attitude that you can't generalize about nature. You can only make judgments about particular simplicities or complexity. You say this law, governing pressure, volume, and temperature, let's say take a simple example, is much simpler. The ideal gas law is much simpler than some of these very complex virial equations which bring in intermolecular forces. Or globalism. I mean, localist, I'm a localist. I want to say, sure, you can say here locally that this is more complex than that in this respect under this description and so on. But the globalist wants to say you can do more than that. You can make reasonably broad generalizations about the simplicity of nature. Okay. So what are the and these guys are globalists, Newton and Einstein and most other people. In fact, anyone who talks about nature itself being simple. What are they arguing? What does Newton say? What argument does Newton give for the claim that nature is simple, which he really depends on for his law of gravity? None. None whatever. Okay? Except perhaps theological, which I'll mention maybe later. Einstein gives a historical-inductive argument. That is, the simple theories have been much more successful empirically than the complex ones, and he argues inductively that this will continue, and then he argues from this to the simplicity of nature, the simplicity of mathematically formulated theories to the simplicity of nature. Kind of inductive argument. Okay, let's see what happens. There, that's the Einstein idea. All right. Now, I want to assess the global argument. Well, I'll do so in a moment when considering the evidential claim that it's reasonable to assume from the fact that a theory is simple that it's true. But before I do that, I want to tell you that neither Newton nor Einstein is in a position to use this inductive argument for the simplicity of nature. Why? Why can't either of them really use that? Because in both cases it's going to be circular. Newton justifies induction. How does he, when he gives you the third rule of arguing from the fact that certain bodies have certain properties observed to, therefore, all bodies do, Newton justifies that by saying nature is simple. And so he can't use induction to justify simplicity because he's got simplicity to justify induction. So he can't do that. And Einstein, following Duhem says that hypotheses are underdetermined by the evidence, and you must employ simplicity then. If you've got a bunch of inductively supported hypotheses, you must, because this underdetermines the truth of the hypothesis that you're considering, you must invoke simplicity. So he's not in a position to use an inductive argument for simplicity. All right. Now let me turn to, so much for the claim that nature is simple, which is not the popular claim today, although I did see a TED lecture by Murray Gell-Mann in which he began putting on the board one big statement from Newton saying nature is simple, and he had it up there the whole time during the lecture to remind us of this important truth. Okay, so the more popular claim these days is that simplicity plays an evidential role. That you can get the evidence that you want and then add simplicity, because simplicity is part of that evidence. Simplicity gives you a reason for believing the hypothesis. Okay, so what is the defense of this claim? Now, I'm not talking just about Newton and Einstein. I'm talking about, most philosophers who invoke simplicity as part of the argument. No defense. That's one idea. It's basic. None needed. See if I have that here. Yeah, well, here's the logical claim. If a theory is compatible with the available evidence, then its simplicity provides at least some epistemic reason for believing the theory. Okay? All right. Well, Newton was one of those philosophers like Descartes who loved God, and he brings God in whenever he's, whenever he can't figure out what's going on. At the end of the Principia, he brings God in to explain why the planets revolve the way they do, on the same plane and in the same direction. There's a probabilistic defense of simplicity, and I don't know if I'll have time to go over it, but the important defense that I want to consider is the inductive argument. And let's see if I have it here. Empirical, inductive, but okay. The core idea is historically simple theories have been much more empirically successful than complex ones. Their predictions, explanations, calculations have been much better experimentally confirmed, and so on. All right, that's the argument. It's a meta-inductive argument. I don't much like meta-inductive arguments at all. Just for the sake of, argument, let's go along with it and see how far we can get. Okay? Can we construct an inductive test for the evidential value of simplicity? Well, there are lots of problems here in doing so. So let's look at the problems and see how we can solve them. I mentioned some of these different respects, levels, etc., with respect to which a theory can be simple. Which ones should we appeal to? Let's say at least several. So if a theory has several of the respects, levels, and so on, at which, with respect to which it's simple, then let's call it a simple theory. Okay. But there's also a selection bias problem, that simpler theories may be easier to test and modify, and complex theories much harder. So they may not have been tested sufficiently. We want to consider theories that have been tested equally well. Then the next question is, let's see if I have all this. Yeah, confirmed when? Confirmed when they were first proposed, or confirmed by evidence we have now? I think we want to look at the success of the theory in terms of what we know now, not back in 1786 or whatever. Then, on top of this, there's the Loudon pessimistic induction problem. How many people know about the Loudon pessimistic induction? Well, Loudon, who was both a historian and philosopher, went through various examples of theories that were widely accepted and very successful when they were proposed and then refuted later on. We got into lots of problems later on. And so he makes this meta-induction that all theories eventually are going to turn out to be false. So that's the pessimistic induction. Okay. But let's not worry about all these things. I mean, they are worrisome, but let's say, okay, let's move ahead. Let's try an inductive test, a purely imaginary case. If I can get it here. Can we construct it? Okay, let's try it. It's a fictional, purely fictional case of what you had to do if you were trying to show this meta-induction that simple theories tend to work better and tend to be more successful than complex theories. So let's start this way. I don't have it on the way I want it on the slide here. We have a team of experts, including scientists and historians of science, identify theories throughout the history of science that are well tested, like today's standards. And then we ask the experts to determine for each well-tested theory whether it is simple, in certain important respects, complex, or not particularly one or the other. We then ask the experts to determine for each well-tested theory whether or not, or the extent to which it has been empirically successful. Of course, in doing these things, the experts have to have some consensus on what is to count as well-tested, simple, and empirically successful. That's one of the problems in all this. Okay, suppose that the simple, well-tested theories are 2 times as empirically successful as the complex ones, and 1.5 times more successful than the ones that are neither simple nor complex. Okay. Keeping in mind Loudon's problem that most theories in the history of science have turned out to be empirically unsuccessful, let's suppose that 5% of the complex theories chosen are empirically successful today, and 7.5% that neither simple nor complex class are, and 10% of the simple theories are successful. All right? So a good Bayesian might say that's an increase in probability. So the fact that a theory is simple is at least some evidence that it's empirically successful, and perhaps even true. Well, I don't find this very comforting or persuasive. It's completely fanciful, first of all. No such test has ever been done. It would be difficult, secondly, it would be difficult to carry out, especially due to the problems mentioned earlier, having to do with the fact that different parts of the theory can be simple or complex. Even forgetting these problems, the strength of the inductive conclusion that simple theories are more successful is quite minimal. 5%, 10%, whatever. Bayesian increase in probability, especially when the probabilities are so low, provide little, if any, guide to belief. I mean, if I buy one ticket in a fair lottery, to use an example I've used over many years, if I buy one ticket, I've increased the probability that I'm going to win from 0 to 1 over whatever the number of tickets are, 1 over 100 or 1 over 1 million or whatever. That's no reason to think I'm going to win. If I just own one ticket, it's probably a good reason to think I'm going to lose. Most important, it is quite possible that a test of the sort I imagine will be inconclusive or indeed negative. Often as theories become more complex, they become closer to the truth or to experimental results. They become more empirically successful as they become more complex. Examples from one element from time of Thales, that's a very simple theory. There's just one element, namely water. To 4 elements for Aristotle, air, fire, whatever it is in water, earth and water, and to 118 today. And we think our theory is better than Thales' theory. So the more usually you add complexities because you want to get it right. All right. Now, what I want to do is to return to Newton. And I want to say something about Newton's famous but controversial argument for the law of gravity, because there is the first time he appeals directly to the simplicity of nature. Now, Newton's 4 rules were the ones I put up here before. Let's see if I can get them back again. That's rules 3 and 4. There's 1 and 2. Okay. Look, at the beginning of the book 3 of the Principia, Newton starts with these rules that are going to be crucial to him for arguing for his law of gravity. Then follow 6, what he calls phenomena, pertaining to the motions of the planets, that they all obey, he didn't call them that, but they all obey Kepler's laws of motion. And then he starts with his so-called propositions, or theorems, he calls them both. And propositions 1 through 3 say that the forces acting to keep the moons of Saturn and Jupiter, he starts with the moons of Saturn and Jupiter, the known moon, the forces acting to keep these moons and all the planets in their orbits are inverse square forces. He gets these ideas, these propositions, from the phenomena, the Keplerian phenomena, and theorems he's already proved in book 1. There's no mention of simplicity here. The first time he mentioned simplicity, or the simplicity-based rule, no mention of the rules here. The first time he mentions the rules is in Proposition 4, which is the most crucial proposition in the proof, or at least so far. And he argues, and this is important, he argues that the force required to keep our moon in its orbit around us, around the Earth, is the same force as the one that causes bodies near the Earth to fall to the Earth. Okay? It's not just the same type of force, not just an inverse square force, and not just a central force, which is directed towards the body, which bodies fall, but it's the same force. And how does he argue for this? Well, he argues that he argues from facts, known facts about the circumference of the Earth and other facts about the motion of the moon around the Earth, that if the moon were suddenly to lose its inertial motion and fall toward the Earth, he figures out mathematically from these other assumptions, he figures out how fast it would fall. If it came near the tops of the highest mountains on the Earth. And the figure he gets is exactly the same acceleration as what happened if a body were to drop from the tops of these mountains. And that's a spectacular derivation. Which means that not only is it's a central inverse square force, but the actual magnitude of the force keeping the moon in its orbit is the same as the magnitude of the force which causes bodies, unsupported bodies, to fall to the Earth. All right. So this is what he gets in that Rule 4. Now, so he's got one force, not two. Okay. All right. Now, so far, simplicity is not in there. He's got the actual data to prove from the magnitude of the acceleration to the magnitude of the force. Okay. So he's got one force, not two. If simplicity were driving this inference, then why didn't he bring it up earlier? When he's got, all the force operating to keep the planets in their orbits are all inverse square central forces. He didn't because according to his Rule 1, if the effects are the same, by simplicity, you're to invoke the same cause, not the same type of cause, but the actual same cause, force of gravity. But he doesn't do it there. And the reason he doesn't do it there is because he doesn't have the data yet. He doesn't have the experimental results. Once he gets the data about how fast the moon would fall to the Earth, and he knows how fast bodies near the Earth fall to the Earth, then he doesn't need simplicity. And I think this is so in general. Now, what he does, very curiously, is say, look, after proving this remarkable theorem, he says, look, therefore, by simplicity, the moons of Jupiter, if these moons were to fall towards Jupiter, the way our moon is imagined to fall to the Earth, they would fall with the same rate of acceleration as bodies near Jupiter fall towards Jupiter. He has no data on what the moons of Jupiter would do. He doesn't know what the rate of acceleration is on Jupiter or on Saturn, the two cases he takes up. He doesn't know that, so he appeals right away to simplicity. By simplicity, since everything is, nature is constant, the same all over, I'm going to infer that Saturn works the same way, and Jupiter works the same way, and the planets work the same way if they were to fall toward the sun, and so forth. So simplicity is carrying a very heavy weight here. But we might say, Sir Isaac, you don't have the data in these cases to show how bodies would fall toward the center of the body. You do on the Earth, and that's what makes the argument convincing. You don't on these other cases, which makes the argument much less convincing. It's a great speculation, and I use this as an example of Newton speculating like mad, even though he's claiming not to do so. All right. Let me give you an analogy, a simple analogy. A drug testing example. Okay? Suppose a drug company wants to test the effectiveness of a drug. And the results are promising, but the sample that they've used is not big or varied enough. The drug company says to the FDA, Federal Drug Administration in the US, it was effective, this drug was effective in this sample, whatever it is, 100 people and so on. And the simplest hypothesis is that it will be effective generally. It's simpler than the hypothesis that is effective only in limited cases, or the hypothesis that those in the sample had their symptoms relieved by different causes, not the drug, and so on. These are all complex hypotheses. The simplest one is that the drug was produced the reduction in symptoms. And the drug company invokes simplicity as part of the evidence for the claim. What do you think the FDA does? It says, more and better testing, not simplicity. Simplicity is no argument here. We want you to test it on a much larger and more varied population. Not approved. Now the second example, same thing, but the drug company goes back and tests the effectiveness on an appropriately large and varied sample under good conditions. And the drug is very effective in this much larger, carefully picked sample. The drug company then makes the inference that the drug will be effective for the general population, adding that it is the simplest hypothesis. Okay? Now, the FDA approves the drug not because of the simplicity of the hypothesis, but because of the strength of the tests. And I think that's the rational thing to do. Simplicity is irrelevant here. And I think this is, if you don't mind me giving this as an analogy with Newton, that's what you want. If you really want to get the information that Newton didn't have, then you should do that and instead of just appealing to simplicity here. So if you're really a very strict inductivist here, you might say to Sir Isaac, I'm going to wait until you test these things on the moons of Jupiter and Saturn before I believe what you believe about the truth of the law of gravity. All right. Let me give you a very different conclusion here. And to do so, I'm going to turn to one of my great heroes, another British dude called James Clerk Maxwell. Okay. Now Maxwell, of course, you probably recognize as the father of the modern theory of the electromagnetic field. But his other contribution, for which he was even more known when he wrote it in the 1860s and 70s, was his contribution to the kinetic theory of gases. So the kinetic theory, to remind you, says that gases are composed of molecules in rapid motion, and his first paper in 1860 said, look, there's so many of the properties of gases are known in terms of gas laws that we need to try to explain why these gas laws hold, to simplify everything. And so he does so because he's a mechanical philosopher. He believes that, at least the first try you make is in terms of bodies with mass and motion, obeying Newtonian laws. So he introduces a set of simple hypotheses here. He says gases are composed of molecules. These molecules are in rapid motion. They don't have irregular shapes. They have simple shapes. They move in straight lines. They have perfectly elastic collisions with each other or with the sides of the container. So the total kinetic energy before is equal to the total kinetic energy after the collision. Now, Maxwell makes it clear that he's simplifying here. He's not claiming that molecules, that actual molecules are like this. But he's saying in order to present a theory, a molecular theory, which was not accepted by everyone, it was people by Maxwell's time were very suspicious about the caloric theory of heat, and here was a guy claiming that it's not, heat is not a substance, it has to do with the motions of the molecules. And again, these were spherical molecules. He makes it clear that he's not inferring the truth or the probability of the theory because it's simple. Simplicity for him was, in this case, was not an epistemic virtue. It was a pragmatic virtue. It was a way of making it easier to do mathematical computations. And if you had said to Maxwell, hey, look, the fact that it's a simple theory is some reason to believe that it's true, he would laugh at you. Because he knew these were simplicities, and in fact, he got some wrong results. He got it wrong. His worst one was about the ratio of specific heats of gases, which he got very wrong, and he admitted it. And in effect, he's saying, look, I'm trying to work out the possibility of a mechanical theory of gases. So I'm not concerned with whether the darn thing is true. I just want to know whether it's possible to explain gaseous behavior, known gaseous behavior, in mechanical terms. We just have forces acting on things. And I'm moving molecules, and I'm not worried about the shape of the molecule. I'm not worried about whether they lose some energy in collision, because it would be much easier to calculate if they don't. So as a result of this, he produced his most astounding result, which is still used today, and that's Maxwell's distribution law for molecular velocity. The derivation that he gave of the law in 1860 is pretty much the one that we use today in teaching the molecular distribution, because Maxwell was the first physicist to introduce statistics and probability into physics. So, look, there's a tension. I don't know how much of this I've skipped. Yeah, this is it. Oh, yeah, Carnap. Okay. There he is. Okay. Look, here's the ideal gas law. Very simple. Pressure times volume equals the constant times the temperature, absolute temperature. And here is a virial equation, which is more complex. It takes into account, in a simple way, the intermolecular forces. But for Maxwell's purposes, he was very happy to derive PV equals RT from his mechanical assumptions. Then he knew he was on to something. He didn't particularly care in that early paper about, and of course this is Van der Waals equation, which is also simplified. I mean, the virial equations today are very complex. And if you're doing what Maxwell wanted to do, that is to see if it's even possible to get a mechanical theory which gives you some of the results that you know are true or approximately true or true under these limited conditions, like PBRT, then you make simple assumptions. And you do so not for epistemic purposes, but to see whether the darn thing will even work to get you what you already know. So I count that as a pragmatic use of simplicity, and as, to me, it's the most important use. So I'm opposed to the usual philosophical view of people like my teacher Quine. Simplicity for him was one of the important epistemic conditions on a theory, and inference to the best explanation in general is based on simplicity. Peter Lipton's book, and even Gil Harman's original article on inference to the best explanation appeal very importantly that the best explanation is the simplest explanation, and the best explanation is the most likely to be true. So all these people who invoke simplicity, including Whewell in the 19th century, all these people who invoke simplicity invoke it as an epistemic virtue and not as a pragmatic virtue. And to me, it's the other way around. It's the important virtue for actual working scientists like Maxwell was its pragmatic importance, not its epistemic. Okay, thank you.